Okay, so let's say you're building a neural network. Right at the start, you've got this huge choice to make. Do you build it out really, really wide, or do you stack it up and make it incredibly deep? Now, it sounds like a simple question, but trust me, the answer has massive consequences for how powerful and efficient your model is going to be. And, the answer, it's probably not what you're thinking.
So what's your first instinct? More width or more depth? I mean, with a name like deep learning, you'd think the answer is obvious, right? Just go deep. But it's really not that straightforward. This is a fundamental architectural choice, pitting two really powerful ideas against each other. And today, we're going to dig into both sides of this debate.
All right, first things first, let's make sure we're on the same page. A wide and shallow network? Think of it like a giant single-story warehouse. It's got very few layers, maybe just one even, but that layer is packed with a ton of neurons. Then you have a narrow and deep network. That's more like a skyscraper. It has lots and lots of layers, one stacked on top of the other, but each floor, each layer has fewer neurons. So, which one is the better design?
So let's actually start with the case for width, which is surprisingly powerful. I know, we hear about deep networks all the time, but it turns out that, at least in theory, a really wide but shallow network can do something, well, pretty amazing.
This slide breaks down a really cool idea. So imagine any smooth curve, any function you want your network to learn. You can get a pretty good approximation of it just by stacking a bunch of little rectangular blocks underneath it, right? Kind of like a Riemann sum from calculus. Well, here's the kicker. A simple single-layer network that uses ReLU activations, which are basically just little on-off switches, is perfectly designed to create exactly one of those rectangular blocks.
And this leads us to something huge, a concept called the universal approximation theorem. What it says is that a neural network with just one hidden layer can, in theory, approximate any continuous function you can dream up. All you have to do is make that layer wide enough. You just keep adding more of those little rectangular blocks, more neurons, until your approximation is basically perfect.
So, problem solved, right? Case closed. If a wide, shallow network can do literally anything, why are we even talking about deep learning? Well, this is where the catch comes in. And believe me, it is a big one. So the problem isn't about what these wide networks can do in theory. It's about the absolutely ridiculous price you have to pay to get them to do it in practice. The theory kind of hides this brutal cost that becomes painfully obvious as soon as you start working with real-world data. And here it is. This is the whole problem right here. The key phrase is in high dimensions. See, most of the data we actually care about, things like images or audio or language, it's all incredibly high dimensional. And to handle that kind of complexity, a shallow network doesn't just need to be wide. It needs to be exponentially wide. And that just becomes impossible fast. This formula from the proof tells the whole story. Don't worry too much about all the symbols. N is the number of neurons you need. L and epsilon are just about how complex the function is and how accurate you want to be. You can play with those. But the real villain here, the absolute killer, is that tiny little d sitting up there in the exponent. That d stands for the dimension of your data. So if you're looking at a tiny 100 by 100 pixel grayscale image, d is 10,000. This means the number of neurons you need isn't just big. It's some number raised to the power of 10,000. It's a number so large it's hard to even comprehend. It's completely impossible from a computational standpoint. This is what we call the curse of dimensionality. Okay, so if width is just cursed by high dimensions, what's the alternative? Well, you guessed it, depth. The real magic of deep networks is how they build complexity. They don't do it by adding more and more neurons side by side. No, they do it by composing functions, by stacking them one on top of the other. Let's walk through a super simple example to see how this works. Imagine a small network, one layer, that just creates this simple little shape, let's call it a triangle function. It's really just a line that has two kinks in it, two places where the slope changes. That's our basic building block. Now, what happens if we add a second layer? Here's the cool part. We take the output of that first layer, our little triangle function, and we feed it into itself as the input for the next layer. And what happens? The number of kinks doubles. We instantly have a more complex function with 4 kinks just by composing the simpler function on top of itself. And if we add a third layer into it again, well, you see the pattern. The complexity doubles again. Now we have 8 kinks. Every single layer we add multiplies the expressive power of the network. This is the heart of it all. Depth gives you exponential growth in complexity with just a linear increase in cost. It's just exponentially more efficient.
Now, to really hammer this home, let's look at the numbers, because they are just mind-blowing. To represent a really complex function, a deep network could do it with just a handful of neurons in each layer. But for a shallow network to achieve the exact same thing, it would need a width of roughly 10 to the 50th power. That's a 1 with 50 zeros after it. It's a number bigger than the number of atoms in our solar system. It's not even a competition. Okay, so the theory seems crystal clear, right? Depth is exponentially better, game over. But theory is one thing. What actually happens when we try to train these massive models out here in the messy real world? So here's kind of a quick recap of the trade-offs on paper. Width is great because it's a universal approximator and it's pretty easy to parallelize across multiple processors. But it's cursed by dimensionality. Depth, on the other hand, is exponentially efficient at representing things. But it's always been way harder to train, thanks to problems like vanishing gradients, where the signal you use for learning gets weaker and weaker as it goes back through all those layers. But then things got weird. A huge study in 2020 on large language models came out with this really surprising result. They found that within a pretty wide range, the specific choice between width and depth didn't really seem to matter all that much. What actually mattered was the total number of parameters and the total amount of compute you threw at the problem. You could have a deep, skinny model or a wide, shallow one, and as long as the parameter count was the same, they performed about the same. So what gives? Well, real-world experiments are just messy. You can change one tiny thing like the learning rate schedule and get a totally different result. It's incredibly difficult to isolate just one variable. The clean, neat theory of what a network can represent gets all tangled up with the messy, practical challenges of actually training it. So if the theory says one thing, and practice gives us a kind of fuzzy, it depends answer, where does that leave us? Well, it suggests we might be asking the wrong question from the start. And that brings us to the final and I think most important takeaway from all of this. The big insight is this. The goal should never be to just build the widest network or the deepest network. The goal is to build a network whose very architecture, its very shape, reflects the natural structure of the data you're feeding it. I mean, think about it for a second. Audio data is sequential, right? One moment in time follows the next. An image has a spatial structure. Pixels are right next to each other in a 2D grid. A generic, fully connected network, no matter how wide or deep you make it, it just sees a giant flat list of numbers. It completely ignores that beautiful inherent structure. And that's just a wildly inefficient way to learn. And that kind of leaves us with a new question to think about. Maybe the debate was never really about wide versus deep. Maybe the more powerful question, the one that's actually led to breakthroughs like convolutional nets for images and transformers for language, is this. What is the fundamental structure of my problem? And how can I build an architecture that has the right assumptions baked in from the very beginning to match the shape of my data?